Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and we were discussing the equation of motion in the moving frame, or the so-called Euler's angles. So we will start our discussion in this module with an example. So the example I have is, we solve the Euler's equation for the free motion of a body with axial symmetry. Right? So let gx3 be the symmetry axis. So this is the symmetry axis such that b is equal to a, and so in free motion we have that k1 is equal to k2 is equal to k3. This is 0, and my Euler's equation is a omega 1 times a minus c times omega 2 omega 3. So this is a free motion case, so the right hand side will be 0 in all the three equations, and this is where two of the principal moments of inertia are equal. So this is for the body with an axial symmetry. So we can similarly write the other two equations. So a omega 2 dot minus c minus a omega 1 omega 3, this is 0, and c omega 3 dot this is equal to 0, and we get that from here, the last equation, we get that omega 3 is a constant which is n. So let me call this n. So this is my vertical component of the angular velocity, or the so-called spin. So this is omega dot with E3. So this is a constant. This is spin. Okay, so this is spin. So then we can continue solving all the other equations. So suppose we introduce, so in these other two equations, so suppose we introduce, let's say omega is a minus c times n by capital A. Right? So if we introduce this quantity, we see that the other two equations are reduced to the following. We have omega 1 dot minus omega 2 is 0, and omega 2 dot plus omega 1 is 0, and if we were to, well, we need to quickly write it again. I think we deleted this. So omega 1 omega 2 equal to 0, and omega 2 dot plus omega 1 is equal to 0. And now if we were to solve this equation simultaneously, we get omega 1 double dot plus omega square omega 1 is 0, and from here we can quickly solve that omega 1 is p sine omega t plus gamma. Well, gamma could be the phase angle, and omega 2 will be the cosine of this same angle, omega t plus gamma, and omega 3 is n, and these are my angular velocities, and my corresponding angular momentum are L1 is a omega 1, and L2 is a omega 2, and L3 is c omega 3, which is Cn. So the result is that the body rotates about the G3 axis with angular velocity omega. So the body rotates about the Gx3 axis with angular velocity omega. Okay, so this is what is happening. So omega is the same omega that we had seen. Okay, so then let us try and look at some problems involving the Euler's angle. So the problem that we have is, Before we look at some example, here are some issues that we would like to discuss. So problems, the issues are problems with involving Euler's angles. So problems in Euler angles, right? So it turns out that the embedded frame, since we are working in the moving frame of the problem, it does not provide us with the original location of the body in the fixed frame or in the inertial frame. So embedded frame does not provide original location, does not provide original location of the body, right? Does not provide original location of the body. And if the applied moment kg is not 0, then the exact solution is difficult. Exact solution is difficult, right? So if there are torques present, then it is harder to solve these Euler angles. So here is one problem that we would like to discuss. The problem is that of the so-called dynamic balancing. Now what this problem is, that suppose we have some rotating rigid body and it is it is pivoted such that it is asymmetric with respect to the pivot points. Now that leads to some problems in the form of oscillations of the pivot itself. Now a case in hand is typically the alignment of the tires of the car. And we have seen that typically when new tires are fitted in the car, they have to go through alignment so that these dynamic balancing problems, they do not arise. So let us look at an example here. So the problem is that we have a case of an axially symmetric body, and let us say this body is rotating about a pivot point. So this is my pivot axis, and the body is asymmetrically pivoted. So it is rotating about the pivot point, asymmetrically pivoted. So we have this angle beta. So case of an axially symmetric body which is smoothly constrained to rotate about a fixed point. Rotate about a fixed point P through G. So this is the point P and this is the point Q. So about a fixed point P through the center of mass G. So through G, but it is inaccurately mounted. It is inaccurately mounted. So this is the case of asymmetric rotation. So this question is, what sort of effects can happen due to the misalignment of these pivots, right? So had beta been 0, then it would have been perfect alignment, and so this is not the case. So this question that we typically ask is, what is the effect this misalignment and alignment have on the pivots, right? So so let us see what happens. So let us say that Gx3 is the symmetry axis. So this is the symmetry axis, and Gx2 is perpendicular to PQ, and Gx1 is along the body. So we have Gx1 is the following. So this is my x1 axis, and x3, and x2 is perpendicular to PQ, so this is my x2 axis, right? And let the body rotate about the point PQ at constant rate lambda. So let the body rotate about PQ at constant lambda, at constant rate lambda, and then the angular velocity components in this G, x1, x2, x3 frame are as follows. We see that omega 1 is negative lambda sine beta, omega 2 is 0, and omega 3 is lambda cos beta. Okay, so these are so because of this misalignment, we have these angles which is arising, cos beta and sine beta. Okay, so then if we substitute in Euler's equation, so substitute in Euler's equations, we see the following. We see that of course, since this is a free motion of the body, we have k1 is equal to k3 equal to 0, but because this moving object is pivoted so that it moves in the plane x1 x3, then we must have the second moment, the second torque component of the torque k2 to be non-zero. It comes out to be a minus c times lambda square sine beta cos beta. Okay, so then in this case the applied moments are constant and embedded in the frame, but they are not constant in the inertial frame. So it turns out, so what is happening is these applied moments are constant in the moving frame, but they are not constant in the inertial frame or the fixed frame. Especially, let's see for example this k2, right? So it turns out due to this non-constant values of the torque, this motion of this asymmetrically pivoted object is subject to certain frequencies of the order lambda square, of the order magnitude lambda square, and these are the asymmetric vibrations which we want to reduce in the balancing of these objects, right? So this is the same. This quantity is something that we wish to avoid, for example, in the car balancing, the tire balancing of the car. So that is a very nice example of dynamic balancing. So tire balancing of cars. Okay. So then I would also like to look at the free motion of an asymmetric body, right? So what have we got? Free motion of an unsymmetric body. Unsymmetric body. Okay, so we have rotation about a fixed axis. So rotation about a fixed axis. So suppose we have a free unsymmetric body B, which is observed, let's say observed from an inertial frame. This is observed from an inertial frame with center of mass G at rest. So the question is it possible for the body to rotate about this axis? So is it possible for the body to rotate about this axis? Okay, so this question is, if such the issue is, if such an axis exists, it must pass through the center of mass. That is certainly true. So what we know that if if such axis exists, then it must pass through the center of mass. Must pass through the center of mass, through center of mass G. So let G, x1, x2, x3 be the principal axis. Be the principal axis of B at G. Right? So this is the principal axis of the body at passing through the center of mass G. So let us say these are my embedded axis. So the Euler's angle apply, because these are my embedded axis. Embedded axis. So the Euler's angle apply. Right? So since the body B is rotating about a fixed axis, the moment of inertia will be constant. So B rotating about fixed axis, then the moment of inertia is constant. Right? So I is constant. Right? So what we have is then omega. So what we have is, since there are also no forces, so this is a case of free motion of the asymmetric body. So since we have free motion, we expect no torques. So we have that the derivative of the angular velocity components, they vanish, or this omega is a constant as well. Okay, so then if we were to use this information, the derivative of omega i's are 0, we could use this in the Euler angles. We see that the following equation emerges. So B minus C omega 2 omega 3 is 0, and similarly C minus A omega 1 omega 3 is 0, and similarly the last one is A minus B omega 1 omega 2, this is 0. And we see that since this is an asymmetric body, we expect that A is not equal to B is not equal to C, and so the conclusion is that either we have omega 2 and omega 3 is 0 and omega 1 is constant, or the set of other two assumptions. So let me write the conclusion here. So the conclusion is that either omega 1 is constant, or omega 2 and omega 3, omega 1 constant and omega 2 equal to omega 3 equal to 0, or we could have omega 2 is constant and omega 1 is equal to omega 3 is equal to 0, and the third is omega 3 is constant and omega 1 is equal to omega 2 is equal to 0. So the result is a free unsymmetric body can rotate about a fixed axis, and symmetric body can rotate about a fixed axis if this axis is one of the principal axes of the body. Right? So a free asymmetric body can rotate about a fixed axis if this axis is one of the three principal axes of rotation, principal axis of the body at G. Okay, so the rotation will have constant angular speed. So the rotation will have constant angular speed. Okay. So this is the conclusion out of these three equations, and now let us look at the most general form of the motion for asymmetric body or unsymmetric body. So general motion. So I am going to just recap and write everything in short. So general motion for unsymmetric unsymmetric body. Okay, so what we saw was, notice that in our Gx1, x2, x3 frame, we had angular momentums LIs. So L1 was A times omega 1, L2 was B times omega 2, and L3 was C times omega 3. So if we use these forms of angular, these are the angular momentum in our Euler's equation, we see that the Euler's equation reduces to the following. So BCL1 dot is equal to B minus C. So rather than writing an equation for omega, we write an equation for LIs. So L2, L3, and then the second equation is AC L2 dot is C minus A L1, L3, and AB L3 dot is A minus B L1, L2. So then I can, we can combine all these three equations to get a common equation from here, multiplying the first equation by L1. So multiplying by L1, multiplying the second equation by L2, and multiplying the third equation by L3, we see, and dividing throughout, we see that L1, L1 dot plus L2, L2 dot plus L3, L3 dot, this is 0. And we see from here we integrate this equation, we get L1 square plus L2 square plus L3 square is a constant, or we call this as L square. And what we get is the components of the angular momentum of the general motion of the free asymmetric body. They are on a sphere. This is also known as the L sphere. The L sphere. And similarly, if we can if we can again look at this set of three equations, we see that this is also equal to BC. Try to add this equation by multiplying and as it is with their corresponding LIs. So we get BC, the same set of three equations will reduce as follows. So BC L1 L1 dot plus AC L2 L2 dot plus AB L3 L3 dot. So this is 0, and then we can divide throughout by ABC, and we see that this is also equal to L1 square by A plus L2 square by B plus L3 square by C. This is we have integrated out. Let me call this as 2T. So momentum. This is the components of momenta divided by the moment of inertia, right? Components of momentum divided by the moment of inertia. So we get that this is our equation of an ellipse. This is an ellipse, and momentum divided by moment of inertia is the kinetic energy. So this is the T ellipse, or the kinetic energy ellipse, ellipsoid, right? So either the L sphere or the T ellipsoid. So what I am trying to say is, for an object which of course has no potential energy, then either the momentum is conserved, it is in the form of the L sphere, or the kinetic energy or the total energy is conserved in the form of T ellipsoid. So this is another way of studying this problem geometrically. So I think I am all out of time in this module, and in the next module we will be looking about the motion of these free asymmetric bodies and look at some examples, some really complicated examples. So thanks so far for listening.